I'm setting up the recording, and I think we may start now. Okay, let's check that everything is visible. Yeah, let's draw an elephant. Let's draw a happy elephant. Yeah, can you see what I'm writing?
Now we can see just your whiteboard. Yeah, we can see. We can see.
Okay. Yeah.
Okay.
Yeah. So just a small remark. If it's possible, you may also start the recording to avoid some technical mistakes. So if something happens, I would prefer that there is a reserve recording. So please, if it's possible, if you have enough space on your hard drive, that's a so if it's possible, you may start the recording like me. Okay. So now we move on to continuous time. Let's move on to continuous time. Continuous time. And everything is much more difficult in continuous time. So t will go from 0 up to, normally up to infinity. And we will consider the most important stochastic process in continuous time, winner process. Or it's also called Brownian motion. Brownian motion. So sometimes these terms are used as the same term. Sometimes there is a distinction between Wiener process as a mathematical model and Brownian motion as a physical phenomenon. But sometimes these are just the same thing. So it depends position of the author of the course. So it's exactly the same term, or either we say that this is a mathematical model and this is what happens in real life. But I do not pay attention to this subtle difference. Okay, winner process. So let's draw first.
Can I ask a question? So
yes.
Could you please tell about some applications of like continuous time analysis? Because in digital world, like we have no ability to measure time continuously, and we always work with discrete cases.
Yes, we always work in. So yes, I understand that in real life we always work with discrete observations. Yeah, the memory of computer is finite, and we can have, let's say, 2 million of observations, but not the continuity of them. Yes, but it makes things a little bit easy to study. So we will price European financial claims. So what will be our main real life goal? Our aim, we will price European type options. So we'll price, and probably American type options too. So that's our real life application. And why it's better to work in continuous time and not in discrete time? Things are easier. For example, if you study just the function like y equal to x, you draw it normally. You consider a real line and you draw here y equal to x. You normally, when we speak about functions, even in school, yeah, you do not say, our function is defined on rational numbers only. It's easy to say that our function is defined everywhere. Yeah, for all real numbers, it's easy to work with a function that is defined on real numbers than a function that is defined on rational numbers. Yeah, there are no gaps. We may discuss continuity. So basically, our real life application will be pricing European and maybe American type options. And why it's better to study continuous time than discrete time, many formulas, many expressions are easier. And the difference between continuous case and the discrete case is pretty small, yeah. Because in real life, we can, let's say, make a deal at every moment of time. Yeah, we can make a deal at every moment of time. We can say, oh, tomorrow at 12 o'clock, I will buy a share, or I will sell something, or I may buy or sell at 2 p.m. 0.5. So that's a good simple idea that let's consider time as a continuous real variable. Okay, so real numbers are easy to work with. So basically, these 2 points. That's why we study continuous time. So it has real life applications and it's easy to work with. So basically that's the main reason. Okay, let's move on. Okay, first let's draw the Brownian motion and then let's formally state all the properties, and then we will transform the Brownian motion to describe the price of a share. Brownian motion looks like this. It's extremely jiggly. So it's extremely something like this. This is T, this is W of T. And formal assumptions are the following. So definition. First assumption, W0 is 0. Yeah, you may see it on the plot. Okay, second assumption, the WE minus WS, we assume that T is bigger or equal to S. This change may be positive, may be negative with equal probabilities, and more precisely, it has normal distribution with expected value 0 and variance T minus S. So that's the second assumption. The third assumption, that increments, so let's state it in words, increments are independent, or we may write it differently, future increment is independent of all past information. So we may state the third assumption in many ways. So we may say, for example, that increments are independent, or future increment is independent of all the past information. What do I mean? Increments are independent. If I consider real line, that is time, and I consider some time intervals from A1 to B1, from A2 to B2, from A3 to B3, and so on from AK to BK. Yeah, I consider these intervals, and these time intervals are non-overlapping, but they may touch each other. So B1 is less than A2, less than B2, less than A3, less than. So they may touch each other, but they may not overlap. Yeah, so this is not possible. So that overlapping is not possible. Yeah. So that's a bad case. And if I consider these non-overlapping time intervals, and if I consider the increment of Brownian motion on each time interval, so I consider that D1 will be Brownian motion at B1 minus Brownian motion at A1. Difference 2 will be Brownian motion B2 minus Brownian motion. Oops, sorry, B2, Brownian motion.
I have a question.
Yeah.
Do I understand that when we talk about increments are independent, we do mean like VT means VC? WT, I mean.
No. I mean these D1, D2, and so on, these differences are independent.
So we cannot say that like VT minus VS is independent. We talk about these differences for each one, right?
Okay, let's first discuss this on the plot. Okay, let's discuss this on the plot first. Yeah, just a moment. So I have some, let's imagine 3 non-overlapping intervals. Okay, I have 3 intervals from A1 to B1, from A2 to B2, from A3 to B3. And this is my plot of my winner process. Okay, and I have the increments by how much the winner process has changed. Yeah, so here it went down. Yeah, this is D1. It went down during the first time interval. During the second time interval, my winner process went up. Yeah. During the third time interval, my winner process went down. Yeah. And these random variables D1, D2, D3 are independent. So if you know that, for example, during the first months, Brownian motion has decreased by 20, you have no information about future increments. So maybe it will go up, maybe it will go down. The information about past increments is useless to predict future increments. Yeah. Okay.
Yeah.
So these random variables, they are called increments.
Okay, and what then which is VT means VS mean?
WT minus is also an increment.
WT.
Yeah, that's an increment too. So if we go back, yeah, that's an increment, but that's one increment. Yeah, that's one increment. And when we speak about independently, we should have 2 increments at least. Yeah, we can say about D1, D2. So we need 2 or 3 or more increments to say they are independent. That's only one increment. Yeah, it's one.
So we can say that this statement increments are independent could be written the same as for any T and S, VT minus VS.
No, you should have many increments to. So that's
yeah.
You should have. That's why I have introduced many increments. Yeah, I need many time intervals. So that's only one change. Yeah, that's just this is just one increment. Yeah.
Okay, I got it. Thank you.
Yeah, that's great.
Yeah.
Please be active and ask questions. That's I'm really grateful to you for your questions.
No, I just think maybe I misunderstood the lecture because I have written like VT minus VS, like all increments are independent. That is why I thought it is for all increments. Yeah.
Yeah. But increments is so that increments. Yeah, many increments. Okay. So now let's go on. Or we may also say the third assumption. Maybe we can say differently. We can say something like this. So the third assumption maybe. So that's. Yeah, these 3a. Yeah, this is 3a, and I may say differently with sigma algebras. And so I may say this assumption without sigma algebras, but some authors prefer to express the same idea differently. That if you have observed something in the past, you have no information about future changes of prices, future changes of Brownian motion. Okay, so there is a different version. So 3a is completely equivalent to assumption 3b, but 3b uses sigma algebra. It's a little bit more difficult to get, but let's at least say it. Okay, the assumption 3b says, okay, let's ft will be sigma algebra generated by all ws for s less than t. So what does it mean? Yeah, this sigma algebra contains all the events that can be stated in terms of past values of Wiener process. So what does it mean? Ft sigma algebra generated by all past values. So that means, for example, yeah, F5 contains, so let's consider F5. F5 contains something like W3 is less than W.4. This event belongs to F5, yeah? So at time moment 5, you know all past values of Wiener process, so you know whether this happened or not happened, yeah? Or, for example, W3 is bigger than W7. This event does not belong to sigma algebra F5, yeah? So F5 contains all the events that can be stated in terms of values of Wiener process before time moment 5, yeah? For example, W3 plus W4 is less than, let's say, W2. This event belongs to F5. And I don't know, W7 divided by W5 is bigger than 2. This does not belong to sigma algebra F5. Yeah, that's okay. Ft. Sigma algebra that is generated by all values of the Wiener process before time t.
Can I ask to provide some examples of elements of F5?
Yeah, they are. This is an element of F5. This is an element of F5.
Ah, okay, I got. Then okay, I got it.
So F5 is a collection of events that can be stated. Yeah, you can state can be stated using values of ws for s less than 5, yeah, or equal to 5.
And like just a quick clarification, just a reformulation of assumption about independent increments, right?
Sorry?
So it's just a reformulation of
yeah, we are trying to do. We haven't finished.
Right?
Yeah, we are trying to do. We are trying to do. And this 3a is equivalent to 3b. 3b says WT minus WS is independent of sigma algebra S for T big or equal to S. So that's another assumption. Yeah. So, and that's equivalent to 3A. That D1, D2, D3, dk are independent. That's not easy to prove, so we will not, or no, we will, I think we will not go into details of the proof, are independent. So there are two versions of this assumption. Yeah. For example, 3b says that, for example, W7 minus W5, you can't predict the future change. This future change is independent of W5. Yeah. For example, yeah. For example. Is it clear or not? So the definition, or that's horrible.
That's clear.
Okay.
I do suppose, yeah, that's clear.
Okay, just a small remark. How can be so? Just a small remark. Probably this is random variable. Yeah, this is random variable. Random variable, and this is a collection of events. Yeah. What does it mean that a random variable is independent? And here I have not a random variable, but collection of events. They are object of different type. Yeah, this is random variable, and this is a big, enormously big list of events. There are so much events, infinitely many, so they are uncountable sets. So there are many events in this sigma algebra. How we may discuss independency of a random variable from a collection of events. Yeah. So what does it mean? Maybe I will just point out how we may discuss independency of objects of different type. Yeah, that's easy. We just transform them into objects of same type. Yeah. Probably you know what do we mean by events A and B are independent. So that means probability of A cap B is equal to probability of A times probability of B. Yeah. And basically, when I say random variable X is independent of F, sigma algebra of some sigma algebra F. How can I give a meaning to this to this statement? I may say, okay, I have sigma algebra F. Yeah, F is a collection of events. I may transform X into collection of events too. Yeah, I may go from X, go to sigma of X. Yeah, this is random variable, and this is the list of all events that can be stated in terms of x. Yeah, for example, x is less than 5, x squared is bigger than 7, and so on. Yeah, and I may say that so my statement basically says any event A from sigma of x is independent from is independent with any b from f. Yeah. So basically, this means that if I can state any events in terms of this difference, W7 minus W5 is independent of any event that is included in sigma algebra F5. So for example, what does it mean? Something like W7 minus W5 bigger than 3, this event is independent of any event from F5. For example, W4 is more than 2 times W3, because this event belongs to sigma of W7 minus W5, and this event belongs to F5. So any event that can be stated in terms of the difference in terms of the increment W7 minus W5 is independent of any increment of any event that can be stated that is present in F5. Yeah, example. So what do we mean by this statement precisely? And finally, so basically this assumption says future increments are independent. So you can't predict future increments of Brownian motion. Yeah. The best point prediction that the future increment will be 0. And finally, the last assumption. So maybe it would be better to write them near, but okay. So the last assumption that pass, the probability that the pass, the trajectory of WT is continuous. That's probability is 1. Okay, so we have 4 assumptions. Yeah. And we state 1, 2, 3, and let's process. So number 4 will be later. Be on the next page. Now we have all the 4 assumptions, and let's calculate something. Okay, let's solve some exercises. Exercise number 1, let's calculate expected value of W7, variance of W7, covariance of W7, W10, expected value of W7 times W10. Expected value of W10 given W7, variance of W10 given W7. I think that's enough. For the moment. And all my calculations are based on assumptions. So I will use only 4 assumptions. Yeah. to calculate everything I have. Okay, let's start with the first one. Who can guess the value of W7? The expected value of W7 is anyone? That's an easy question.
Okay. Is it V7?
No. Expected value.
Like
okay, we know that W00, that's assumption 1. Yeah. So that's assumption 1. So basically I can write W7 minus W0. But according to assumption 2, W7 minus W0, if I use assumption 2, I have a normal distribution with mean 0 and variance 7. Yeah. I may copy my assumptions here. Let me copy my assumptions. Yeah, these are my assumptions. These are the two assumptions I need for the moment.
7 and W, and it will be also normal distribution, normally distributed difference.
Yeah.
It will be something minus 0, and it will be equal to 0, and it's still 0.
Yeah. So if I look at my assumptions, this W7 minus W0 is N0 7 minus 0. Yeah. I consider T equal to 7 and S equal to 0. And hence the expected value is 0. Yeah. So this is expected value of WT minus WS. And this is a variance of WT minus WS. Yeah. Okay, what is the variance of W7? By the same logic, I can write variance of W7 minus W0. And variance of W7 minus W0 is just T minus S. By assumption 2, it's T minus S. It's 7 minus 0. It's 7. Yeah, that's okay.
Why?
That's assumption. So that's assumption. I believe in this. So that's the definition of the winner process. So W7 minus W0 has normal distribution 0, 7 minus 0. So that's the definition. Yeah.
So the variance like stacks up with the more members.
Yeah. Because basically in one day, I believe that the price of, let's say, of dollar may go up by 2 rubles. And in 1 year, I believe that the price of dollar may go up or go down by 50 rubles. Yeah, that's normal. That's a more or less realistic assumption that the bigger is time interval, the bigger is the variance. Yeah, that's a realistic assumption. Yeah, if you consider 2 time intervals, one interval is small, other interval is big, and I believe that on bigger time interval, bigger changes are possible. Yeah, that's okay.
Yeah. Okay. Thanks.
Does does Brownian motion assumes that distance between like Wi and Wi plus 1 has a mean of 1?
No, mean the expected value is 0. Yeah, the expected value is 0.
But I'm talking about like distance between like point W T and WT plus 1.
WT plus 1
well,
minus
I guess
WT
I could reformulate my
normal,
question
0, 1.
To why our variances are like stacking in such a way that for every step we take, we add 1 to our variance? Like, why exactly 1? Why not like 5?
We start with this process. We will transform it. So basically, you can. So we start with this process, and then obviously we can scale it. Yeah. For example, yes, that's not the final point of our discussion. Yeah. Obviously, you can consider the process YT, that is 5 times WT plus, let's say, 6. So you may consider that T, that is 5T times WT plus 7. And you can study many more processes. So that's a starting point. Yeah.
Okay,
that's not
thank you. So
the
it's
only
like
process in continuous time. Yeah. You may scale it.
yeah.
And here the variance of ZT will change with T. So you may scale it all for something more or less realistic. The price of a share is modeled something like as 0 times exponent of alpha WT plus beta T. So for some realistic model,
Okay.
you need positive prices. Yeah. And, so basically, WT is a starting point. Yeah. That's not the final model for the price of a share or price of a currency. But that's already is more or less a realistic one, something like exponent. So that's more or less realistic. Okay, let's move on. But to study interesting functions of Wiener process, first we need to study the properties of Wiener process itself. Okay, covariance. For this we will often use the trick that. So the trick we will often use is the following. Future value is current value plus increment. So that's very easy idea, but in many applications, in many calculations of this simple idea will allow us to calculate complex things. Well, that's a very simple idea. Future value of process is its current value plus the increment. So ID is very simple. Now let's calculate everything we have here using this simple idea. Okay, let's calculate covariance of W7 and W10. And I say, oh, okay, W10 is a future value. So imagine that now. So now T is equal to 7 and T is equal to 10 is a future, some time moment in the future. And I can say, okay, covariance of W7, I just will decompose future value as current value plus change. Yeah, that's a very simple idea. From a mathematical viewpoint, it's trivial. Yeah, I add W7 and I subtract W7, so nothing changes. But this is very simple idea, but it's very powerful. I will calculate in a few seconds the result. Yeah, I remember that covariance of RS plus S plus S W, it's a bad name, RSL is linear, covariance is linear, so it's covariance of RS plus covariance of R and L. Yeah, we have linearity of covariance, like expected value is linear, covariance is linear with respect to both arguments. And hence, I see that my covariance is covariance of W7, W7, plus covariance of W7 with this delta. Yeah, this is just the first term is just variance of W7, and we know that is 7, and this term is 0. Yeah, why 0? Because we have assumption 3. Yeah, we have assumption 3. Assumption 3b says that W10 minus W7 is independent of F7. So everything that you know at time moment 7 about the winner process gives you no information about future changes. Yeah. So future change, future increment, the change of the price during tomorrow, we assume for the moment that it's independent of all we know in the past. Okay, so I've calculated the covariance of W7 and W10. Any questions?
Not yet.
Okay. So just to check that everyone is can get the idea, what is covariance of W, let's say 123 and W45? What is this covariance?
So it is 0?
No, that's not an
45?
Yeah, 45. Because I may say, okay, so that's covariance of W45 plus increment. W1, 2, 3, minus 45. That is increment. And that is increment. And increment is independent with W45. I can omit it. Yeah, so that's covariance of W45, W45, and we get 45.
Wait, so we say that covariance of V and increment will be equal to 0, right? In general.
Future increment,
and then
future, not past.
Future increment.
If you consider the covariance of W5 minus W4 and W5, that will not be equal to 0. But if you consider covariance of the future increment, so that will be 0. So that's important. Future increment and past information, but that's not future increment. It's past increment. I have observed it at moment 5.
I see.
Yeah, so that's
Got
future increment.
And then if we want,
in my assumption 3, that's very important. So here I say that future increment, is independent. So future increment, So that's for T. So that's important here, of S. So that's not FT, that's FS. Feel free to ask questions.
And otherwise, when we just meet random V's in the covariance, then we try to write them as increment.
We can always decompose everything. So it may take a little bit of time. So if you think about something like expected value, so it may, you can always decompose it into increments. So if you'd like to calculate covariance of, W5 plus 6, W7 with W, let's say 6, you can always you can always go to differences, So first I start with, okay, let's say that this is future, I must say covariance of W5 and W6 plus 6 covariance of W7 and W6, and then just linearity of covariance. And then in the first covariance, I decompose W6 like future value, will be covariance of W5, W6 minus W5 plus W5. And here I consider 7 as a future value. 7 W6 plus W7 minus W6 with W6. And it will be 5 plus 6 times 6. And it will be 35. Okay, let's continue. By the same logic, covariance of WT, WS is expected value of WT, WS minus expected value of WT times expected value of WS. We have already proven that this is 0. Hence, covariance is equal to expected value of the product in our case. And the next question we have finished with. The next question is just covariance of W7, W10, and it's 7. Okay, let's move on to the next question. The next question, as far as I remember, was expected value of W10 given W7. Probably you can guess we use the same trick. Decompose the future value into past value plus increment. So this is future, this is current information. So we say expected value of W7 plus increment, W10 minus W7. From mathematical viewpoint, I have done nothing. So that's trivial transformation from the mathematical viewpoint, but from like sense of my action is just decompose future into current value plus change plus increment. So this is current value, that is increment, yeah. Increment. So that's W7 is known, yeah. So hence I got W7 plus expected value of W10 minus W7 given W7. They are independent by 3b. If they are independent, my information is useless. I just replace conditional expected value by unconditional expected value because random variables are independent, and hence my information is useless. I can omit my information. I can remove it. I have no useful information, and that is 0. That is 0. Oh, sorry, W7 plus. And we got obvious result, yeah. So the best prediction of winner process 3 days later is a current value. Yeah, the best prediction of the winner process 3 days later, or 5 days later, or 10 days later is its current value. Okay, what else do we have? As far as I remember, we have variance. Yeah, let's move on to the variance. Variance of W10 given W7. Probably you guessed the trick. The trick is to represent future value as a sum of current value plus change. Okay, we've got variance of W7 plus W10 minus W7 given W7. Okay, that value is fixed. Yeah, that value is fixed. Yeah, we have W7 to the right, in the right side of the conditioning bar. Yeah, we know W7, so we consider it as a fixed non-random variable, so it doesn't influence the the variance. So we just remove it. So it's variance of W10 minus W7 given W7. Once again, the increment is dependent of the past, independent of the past value. So I replace conditional variance by unconditional usual variance. And I use assumption that W10 minus W7 by assumption 2 has normal distribution with mean 0 and variance 10 minus 7. And hence the variance is equal to 10 minus 7 is equal to 3. Okay. Any questions?
Maybe no questions from me.
Okay, let's. I think we have solved our first exercise. Yeah, this we have done. This we have done. We have done everything. Okay, let's move on to. Let's move on to the next. We can create many martingales based on winner process. So let's consider two martingales. So let's start with two martingales. So the definition of a martingale in continuous time. Definition of a martingale in continuous time. In continuous time. First definition, expected value of, say that some MT t belongs from 0 to infinity continuous time is a martingale. Martingale if expected value of mt plus h given ft is equal to mt, where h is negative. So if you try to predict the future value of a martingale, given current information, ft is a sigma algebra generated by ms for s less than t. So if you know all past values of a stochastic process mt, then your best guess of the future value mt plus h is the current value mt. So that's the definition of a martingale. That's the definition of a martingale. Or more precisely, that's the definition of a martingale in continuous time. That's okay. And now let's consider, let's say that a small theorem, very small. Okay, Wt is a martingale. Wt squared minus t is a martingale. There are many more martingales, but these two, they are important, and maybe the second one is very important. Many calculations will be based on this martingale. So it seems, oh, that's martingale, but it's something technical. But many calculations in stochastic calculus for finance are based on the second martingale. Okay, so let's prove this theorem. Okay, the first point is very easy. If you take the expected value of winner process t plus h given ft, obviously we use the same idea. We decompose the future value as current value plus change, plus wth minus wt given ft. And we say that this is known, this is known. We take it out of the expected value as a known random variable, and that's known random variable. We just take it out, plus expected value of the increment, and by assumption 3b, these are independent.
Sorry, can you please show for a second the theorem once again?
We have 2 points. Wt itself is a martingale, and Wt squared minus t is a martingale.
Okay, thank you very much.
You're welcome. Thank you very much for being active. Okay, they are independent by 3b. So the numbers are not important. So in some books you may number assumptions that I have numbered. So that's not important, the number of the assumptions. Okay, that's WT plus ordinary expected value. As my information is useless, I remove my information, and this is 0, and it's WT, and we have proven that WT is a martingale. Okay, let's consider point B. Let's consider the process xt, that is WT squared minus T. And let's calculate expected value of xt plus h given ft. So,
okay, AB are part of the proof, like first part are the second part of the proof, right? No?
Yeah.
So
we have
AB,
two statements.
yeah,
we have two statements. The first one, this is A, and this is B. Winner process is itself a martingale, and WT squared minus T is a martingale. So on average, they're unpredictable. Yeah, if you know the value of WT, you can predict future increments. You can predict future value, but you can't predict future increments. The best prediction of future increment is 0. Okay, so let's just write. I just plug in and I use the assumptions. I have nothing more than assumptions. Okay. So it will be expected value of WT. Oh, probably you guess, we will say it's XT plus H minus XT. Yeah, the trick is the same. So we move XT out. Yeah, we move XT out, that it's known. Yeah, so the logic of the proof is the same. Known random variable. Xt plus expected value of xt plus h minus xt given ft. Okay, let's focus on this difference. If this difference is 0, then we are done. Okay, so to have a martingale, we need xt. So we need to check that this expected value of future increment, let's calculate it. It's expected value of WT plus H squared minus T plus H minus WT squared minus T given FT. Okay, so we have expected value. Oh, that's a little bit boring. That idea is the same. We decompose future value into current value plus increments. The idea is the same. I will say that it is WT plus H minus WT squared minus H minus WT squared given FT. So I use always the same idea. This is the composition of future value into current value plus increment. So the idea is the same for all the proofs. So I have T and T, they disappear. Open the brackets. WT squared plus WT plus H minus WT squared plus twice WT times WT plus H minus WT minus H minus WT squared given FT.
It seems like, for example, Can we write this the second
first one,
expectation?
second one.
I mean, not after the first one. This is when we meet WT plus H squared minus T plus H minus this.
Yeah.
Can we write this as the difference of two math expectations?
Yes, we can, but it would be, yes, we can. There's a property of expected values. Expected value of a difference is a difference of expected value. You're right, but the problem is that.
But I just know that in the lecture we proved that WT plus H squared minus T plus H by if we know that f of t expectation will be equal to this difference.
Oh, okay. Yeah, if you have proven that in this lecture. Yeah, there are many different ways, but yeah, there are many different proofs. Yeah. Okay, so we are. This will disappear. That is independent of ft. Yeah, that is independent. Now we have expected value of Wt plus H minus Wt squared plus 2 times expected value of Wt plus H minus Wt given Ft. This Wt is known. Yeah, is known. Hence, that's just the variance of Wt plus H minus Wt, this expected value, plus twice Wt expected value of Wt plus H. Oops, sorry, I forgot H minus Wt given Ft minus H. This variance is equal to T plus H minus T, yeah, minus
Sorry,
H.
why does expected value of some variable squared equals to variance of this variable? Shouldn't there be like a minus expected value of a random variable and it's all squared?
Yes, you're completely right. Wt plus, we have assumption 2 that says that Wt minus Ws has normal distribution with mean 0 and variance T minus S, hence Wt plus H minus Wt, according to this assumption, has normal distribution with mean 0 and variance T plus H minus T, and this is 0. You're right, you may subtract 0 squared or add 0 squared. Yeah. As expected value of Wt plus H minus Wt is 0. Okay.
It's now really similar to something that we did on the lecture. Last one.
That's completely equal. And we have twice Wt times expected value of Wt plus H minus Wt, and we got 0. Yeah. Oh, now let's move to something more interesting. Yeah.
Sorry, can I ask a question about this task?
Yeah. What's your question?
How do we define like conditional expectation based on some sigma algebra?
I've missed the beginning of your question. Yes, we are using conditional expected value with respect to sigma algebra. Yeah.
Like, what does it mean to calculate a conditional expectation based on sigma algebra?
What does it mean to calculate conditional expected value?
So I understand the definition of conditional expectation where we like conditioning on some random variable, but when we are conditioning on a sigma algebra, it becomes not really apparent how to do it, like what is the definition, what is the common sense of it.
Basically, sigma algebra represents information. So the first point, you know something. And so expected value means your best prediction. Yeah.
So for example, yes, if I like this formula, I could say yes, like for example, if I know that like y is more than 10, then and I use this formula, right?
Basically, yes. So intuition is following. Intuition, the best point forecast. So the best point forecast of y given knowledge in F. Because sigma algebras, they describe knowledge. Mathematically precise definition is the following. Precise definition. So the best point forecast. Okay, so let's say that expected value of y given F is some random variable. Let's say, let's call it, I don't know, R. Yeah. So first, that's a random variable. First, formal requirement for this random variable. So that's a random variable that satisfies some requirements. The first one, sigma of R is contained in F. Basically, that means you can calculate R using information in F. Yeah. So all the events that can be stated in terms of R, that is less information, that all the events that you have more information, you have enough information to calculate the value of R. Yeah. So that's the first assumption. The second assumption, the prediction error. So that's y minus R. Yeah, the prediction error is independent. No. So the prediction error is linearly independent of what you know. Yeah, the prediction error is linearly independent of any variable you can calculate. Using information in F. Or to be mathematically precise, the covariance of y minus R and indicator of any event A is 0 for all events in F. And the third assumption, the average prediction error is 0. expected value of y minus r is 0. So that's a formal definition of conditional expected value. So that's abstract. I see your point, but that works. That's very abstract, but that's how it's defined.
Okay, and usually like sigma algebra in that case is just like
is generated by some random variables. Yeah, and you can use
that would be like formalized in terms of like n
some
variables.
random variables. Yeah, exactly. So
okay, it's now more clear. Thank you.
Okay. Let's calculate something. Yeah, we are here. Now let's. How much time do we have? Oh, we have. Now we have 6 minutes. What we can do in 6 minutes? Okay, let's try to do something interesting. Okay, let's do the time inversion. Time inversion. Inversion. We will not prove this theorem completely. We will not prove this theorem completely, but we will state it and we will partly prove it. Okay, if WT is a winner process, then YT defined as W1 over T multiplied by T bigger than 0 and 0 for T equal to 0 is also a winner process. So let's check some basic properties. So let's check some basic properties that at least there are no. So the honest proof of this theorem is hard, but let's check some basic properties we can check easily. Yeah. So not a proof, but a small check. We know that variance of WT is T, yeah? We know that expected value of WT is 0. So let's check at least these properties of YT. What is the variance of YT? Is variance of T times W1 over T. So it's T squared times variance of W1 over T. So it's T squared times 1 over T. Oops, it's T. So that's a small check though. That's not a full proof, because to have a honest proof, we need to prove all the properties, all the 4 properties. And the hardest part is to prove continuity. Expected value of YT is expected value of T times W1 over T. We take out T and we will get T times 0 is 0. Yeah. So a small check that we have at least the same variance and the same expected value as for winner process. And now using this strange time transformation, so why it's called time inversion, because Y4 is depends on the value of W at time moment 1 divided by 4. Yeah, it's like when T goes up, 1 over T goes back, yeah, in time. So it's called time inversion transformation. Okay, let's, for example, calculate expected value of W7 given W10. So, okay, so that's time is inverse. So I try to predict past values if I know future values. Yeah, I know future value and I try to recover past value. Okay, I say that I can use time inversion. Yeah, I can say that W's, I can say, okay, I will introduce W1 over 7. Yeah, it will be 1 over 7 times W7. Yeah, so I use time inversion. Y1 over 10 will be 1 over 10 times W10. Once again, YT is defined like T times W1 over T. So I use time inversion. Hence, my expected value is equal to expected value of 7 times Y1 over 7 given Y1 over 10. YT is winner process. So I can say expected value of 7 times expected value of 1 at 1 over 7 given Y at 1 over 10. And YT is a martingale. YT is a martingale. And I've got 7 times Y1 over 10. And I go back to W. And I got 7 times 1 over 10 times W10. It's 7 over 10 times W10. And I have calculated expected value using time inversion. Yeah. So that's a powerful trick to make time inversion for some calculations with Brownian motion. The result is more or less intuitive. If that's T, if that's WT, imagine that you start at 0, yeah, and you finished at time 10 at W10, and you know that you start at 0 and you know you're finishing your last point, your last W10, you know it. So there are many trajectories, and there are many trajectories that connect these 2 points. But if you calculate the average of these trajectories here, yeah, the intuition says that expected value of W7 given W10 will be 7 over 10 times W10. So that's more or less intuitive. You just calculate the proportion of time corresponding to 7 if you take 10 as a 100% time interval. Okay, that's a good moment to stop our exposition about winner process. So that's a very hard mathematical object. That's not easy. So you may try to calculate something variance of W7 given W10. And the trick is the same. Yeah, you may use time inversion. Basically, that's all for today. If you have any questions, then don't be shy. Thank you.
Okay, thank you. Goodbye.
For being active.
Have great weekends.
Excuse me, could you please give the intuition behind the time inversion? I didn't really get it.
The intuition behind time inversion is hard. So the intuition behind time inversion is hard. So
like, why do we do it?
Why? So that's not obvious, but the idea is the following. So that seems a little bit like a magic. We have checked only that expected value coincides with the expected value of winner process. We have checked that variance coincides with the variance of winner process. We haven't checked all the properties, but okay, let's describe. So that's the path of WT. And if you draw many paths, many trajectories of WT, so what is an inversion transformation? So inversion transformation is very strange. So this is T. You say something like this. You take, so let's imagine that this is time moment T1. Okay, you keep this value, you keep this point, because Y1 is 1 times W1 over 1 is just W1. Okay, and then you are doing some real magic. You take, so you take this part of trajectory. You take the left part of trajectory. And so this part of trajectory goes from t equal to 0 up to t equal to 1. And the second part of trajectory goes from t equal to 1 up to t equal to plus infinity. So 1 is a time interval from 0 to 1, and the second one is a time interval from 1 to plus infinity. And you just flip these trajectories, you take some strange mirror here. You just take some strange mirror. You just take a mirror here and this mirror is magic because it shrinks the infinite interval into finite interval from 0 to 1, and it expands the interval from 0 to 1 to the interval from 1 to plus infinity. So basically, this infinite trajectory is squashed into a small interval, and the small interval is expanded into infinite interval. And if you do this strange transformation with all, so for example, this point, so that is t, so for example, that is t equal to 2, yeah, roughly. So it will go here into t equal to 1 over 2. So that point will go here. Yeah. And my process will because it's positive there, so it will be positive on the corresponding segment there. So, and you transform with this magic mirror, you transform many trajectories of winner process. So you take
like our D variables. Yeah, we've had a D random variable, which is an increment from W1 to W2, for instance.
Trajectories. No, not random variables. You have the whole trajectory. You have many trajectories. So
no, I mean they scale and.
So you have many trajectories, and using this mirror, you transform all trajectories. So you take the trajectory and you transform it into the you transform all trajectories. So the first trajectory is transformed, the second trajectory is transformed, the third trajectory. So you transform all trajectories. And after this transformation, WT goes to T times. So you transform trajectories, not random variables. Trajectory is a more, so you use this transformation. The trajectory is transformed into trajectories. And you will see basically qualitatively the same picture. They start at 0 and they expand with the same rate They have the same number or average number of crosses with 0. They have basically the same probability of being higher than 5 at time moment 3, and so on. So you will see qualitatively the same picture. These are trajectories of Wiener process, and that are trajectories of Wiener process.
So the time scale stays the same. We do not change it. T on x-axis, I mean.
Yeah, so that's T, yeah. But trajectories are transformed, yeah. So
And
this transformation
of mirrored, like of time inverted process will be 0, right?
Where time inverted process will be 0?
Like probability limit of this mirrored process will be 0, right? Because W0 was 0.
Not exactly. Yeah. The problem is that when you consider W, so if you consider Y, let's say 1 million, yeah, it's 1 million times W1 over 1 million. And this value goes to 0, but that value goes to plus infinity, and the limit is not 0. The limit may be...
But it is a process, and it must tend to 0. Going to the left. Going to the left to the y-axis.
Yeah, going to the left, yeah. Going to the left, it will go to 0, yeah.
Yes, but I was interested about going to the right. Okay, that's interesting.
But to the left, that's okay. If you consider y with some small value, yeah, with some, let's say, 1 tin, yeah. So it will be 0,001 times w tin. And if you consider expected value of 0,001, it would be 0. If you consider variance of y0001, it would be 0,001 squared times variance of w1000, and it will be 0,01 times 1000, and it will be 0,001. And you see that the expected value is 0, and variance will go to 0. And if you have something with expected value, the probability limit of yt when t goes to 0 is indeed 0, because expected value of yt is always 0, and variance of yt goes to 0 as t goes to 0. Yes, it will tend to 0, but it will not tend to 0 at t as t goes to plus infinity, because of this problem, yeah. And if you calculate the variance of y 1 million, this 1 million will be squared, yeah. It will not tend to 0, yeah. It will be squared, so you will have squared here times 1 over, and it is not going to 0.
Okay, variance will be faster than...
Yeah. The variance will increase, and it may be very far from yt, may be very far from 0 when t is big enough, yeah, because variance goes to infinity as t goes to the right, but the variance will go to 0 as t goes to the left, and that's basically the property of Wiener process.
I also wanted
to we somehow limit the...
Okay. Yeah.
You're welcome.
Okay, I wanted to ask in the last exercise why yt was also a martingale.
We have proven this. We have proven that Wt is a martingale, Wt minus t is a martingale. We have proven this. And if we believe in this theorem, yeah, if we believe in this theorem, yeah, if we believe, we haven't proven it, we have just checked that the variance is the same as the variance of winner process, but if we believe in this theorem, it says, the moral of the story, YT is a winner process. So YT is a martingale.
So everything that is a winner process is a martingale, right?
Yeah. Or we may also say that YT squared minus T is a martingale, yeah, because we have proven that something for winner process, and we say YT is a winner process. All results do apply for YT. All results that are valid for WT are valid for YT, because YT is also a winner process. It's dependent of the process WT, they are obviously dependent, but if something is true for WT, the corresponding statement, when you just replace W by Y, is also valid. Yeah, everything you prove. So for example, here we have proven something about, W, the same thing is true for Y, yeah. Every statement, so we have created a new winner process from the old winner process, yeah. Yeah, I may say, by the way, yeah, I may say YT squared minus T is a martingale. Okay, if you have no more questions, then...
And yeah, one more.
Yeah.
One more question. Like in general, could we somehow limit the variance of this process? Because like with the large segments, we lose the precision of predictions. And so could we somehow limit it or limit the variance, or we just could study it? Like, are there any options?
Normally, we work with some modified versions of winner process. So winner process itself is just the starting point for modeling some real phenomenon. So basically, obviously, you can say, let's stop it. Yeah. So normally, you can just say, okay, let's consider something like, so let's say, you may say that, okay, I have reflecting barriers for some currency policy, for some currency regulation policies. You may say, okay, I believe that here I will have the intervention of the central bank and it will not go below this barrier. Yeah. So we say that winner process is a starting point, the first really maybe interesting process in continuous time. Yeah. So you may say that by some central bank policy, the currency rate is in the corridor. Yeah, I have interventions of the central bank here and there, and obviously in this case, I can't leave this corridor, and this is a different process based on the winner process. Yeah, so you may create new processes based on winner process, and they may have a finite variance and so on. So basically, winner process is defined like it's defined. Yeah, the variance of winner process tends to plus infinity, but you can create new processes starting with winner process, and these new processes may have desired properties you'd like to have.
Okay, that's all. Thanks.
Okay, See you next time. Bye-bye.
Okay. Can I ask one more question?
Yeah.
Like, it's about example we were looking at f at 5.
Mm-hmm. No, even before, yeah.
It's just you have written that a collection of events that can be stated using values of vs for s less or equal to 5.
Yeah.
Well, I do not really understand values of vs for s less or equal to than 5. This part.
Imagine
not clear.
imagine that you start observing the values of winner process. So times goes on. So imagine that you start here and you are very attentive. You don't miss, you miss nothing. You just observe the evolution of my process. And this is 5. So here we are. And all you know whether all this event happened or not happened. So for example, this event W2 is less than 3. You know whether it happened or it didn't happen. Yeah.
Mm-hmm.
So if you consider that event W2 bigger than W3 at time moment 5, you know, you have observed and you are sure whether, okay, yes, I have observed this. No, this didn't happen. You know it. And so this belongs to F5. F5 is your knowledge. Yeah.
I see.
So F5 is the list of all the events that are known to you. So you know whether they have happened or they didn't happen. Yeah. So that's by saying that event belongs to F5. I don't say that they happened. I don't say they didn't happen. I say you know whether they happened or not happened.
Okay. I got it. Thank you.
Okay. Thank you for your questions.
I do suppose no.
Yeah.
Thank you for the consultation.
Have a nice weekend. Bye.